All right, ladies and gentlemen, class recording has started. Today, we start looking at the last section of this unit. We're actually going to spill over a little bit into chapter 17 of your book. Chapter 16 was about electric charge, electric force, current, voltage, resistance, circuits, that kind of stuff. We're actually going to spill over a little bit in chapter 17 now and deal with magnets because there are a lot of similarities there. And a lot of the things that we learned in the previous section are going to be applied here in this section when we deal with magnets. Okay? So, first, nothing to write down here, but keep in mind here that the stuff we're going to talk about today, this idea of magnetism, is not a new concept. This isn't like atomic theory or chemical bonding or something like that that has been developed over the past 100 years, 200 years, something like that. The idea of magnets and their use goes back a long, long time because magnets are something that occur naturally out there in the world, right? That people back in ancient Greece, they realized that certain kind of rocks have the ability to orient themselves in a way so that they're always pointing in the same direction. They didn't know why, they just knew it happened. So they used them then to make compasses and navigate and give directions and stuff like that, right? Well, we know now today that those rocks contain an iron compound. Back in the day, they called it lodestone, but now we know that it's a compound called iron oxide. And the iron part is the magnetic part, and it sets itself up with the magnetic field of the Earth. Yes, Trent?
Why does a magnet mess up like a computer or TV?
Hold on to that section. Good question, and we'll talk about it a little bit later. The very last part, Trey, of this outline is why are things magnetic, and that will we can answer that question there. Okay. All right, but just because it's something old doesn't mean it's not something that's relevant, right? Magnets are something that you guys are real familiar with, right? I'm sure a lot of you have magnets on your refrigerator at home, okay? In your locker, if you have like a mirror or a dry erase board in your locker or whatever it is to put things up there. Back when you were a kid, you got those little toys, like you're learning your shapes, that like the triangle goes into triangle space and the circle goes into circle space and stuff like that, right? And they stick there because they're magnetic and stuff like that, right? And through that, you're aware probably of some of the behavior, right? That some things stick together, but then other things push apart. So there's the attraction and the repulsion piece, similar to what we talked about with charges, but for a different reason. Okay? So with that being said, let's talk about some of the basics, right? Magnet. Okay? I think most of us are probably aware that there are two ends to a magnet, right? One of those ends points towards the north pole of the Earth, or the top of the Earth. And we refer to that as the north-seeking pole, or we just call it the North Pole, right? We label it N, right, because it points towards the north pole of the Earth, or the north geographic pole. We should make that distinction. And then the other side of the magnet, right, we call that the South Pole. We label it with an S because it lines itself up with the south geographic pole of the Earth. Okay. So when we refer to the poles, right, we'll talk about the geographic pole and then the magnetic pole. So keep that in mind. There are two different things. So one side of the magnet we call north, one side of the magnet we call south, because the north side points towards the north geographic pole, right, towards Canada and that area, right? And then the south side lines itself up with the south magnetic pole. Yes, Andrew?
Isn't magnet move not the same as wheel move?
Correct. So we'll talk about that in a little bit. If you look on the back, of the outline, there's a picture of the Earth that's got like a back. So we'll talk about that a little bit. All right, good with this? Okay. I think most of you are probably aware, right, that magnets come with two poles, right? Each magnet comes with the North Pole and the South Pole, okay? But what we find out is that North and South poles are not like positive and negative charges. In electricity, we talked about the idea that a positive charge comes from a proton, a negative charge comes from an electron. And you can have a positive charge by itself and a negative charge by itself. But that's not the case with a magnet. That magnets always have two poles. And if you break a magnet, right, if I drop this and it breaks in half, the side that says N won't just be the North Pole, and the side that says S won't just be the South Pole, right? That when we break the magnet, two new poles show up, and each of those halves now has a new North Pole and a new South Pole. They always come in pairs. Like I said, that's different than what we talked about with charge, right? That there is no such thing as a quote-unquote magnetic monopole, right? Or,
Like, what about the magnets are shaped like horseshoes? Like, how is there like a?
they still have a north side and a south side. It's just a little bit different. Just it's basically bent, right? It's kind of a bar magnet that's just bent around, right? So the same idea is there, that one side of that magnet is north and one side of that magnet is south. And if we broke it, we would have another south pole and another north pole that just sort of like automatically show up. Okay? Look good.
When you say it points north and south, does that mean if you drop it, it'll just automatically turn or something?
Yeah, in this case here, okay, so in this case I can put it on the desk and it does this because it's not, the magnetic part isn't the only thing affecting it. It has to deal with friction while it's on the table too. But if I tied this up and hung it from the ceiling, the North Pole would orient itself towards the North Pole of the Earth, and the South Pole would orient itself towards the South Pole of the Earth. Okay? Maybe Monday I'll do that. Benches?
Yeah.
So you guys can go outside today and sit and relax.
Yeah, but
and-
they can't
Snow.
even, parents can't even like turn in here, so I don't
Yeah, it doesn't mean you
understand.
can't sit there.
Why did you sit there? There's no one to-
Well, I mean, like if you're waiting for the bus, like that's where buses pick people
We don't
up.
have buses.
Like for sports teams and stuff.
No, they pick 'em up.
So, no, right in.
Completely not necessary. I don't
But
understand
look,
why.
to answer your question, that if this thing could, if it's allowed to orient itself just in a way where it's under the force of just the magnetic force of the Earth, it would set itself up so that north points north and south points south.
Why you do it right now?
Because I don't have a string to hold it up with. So I mean, I do over there, but I want to get through this. So, all right. Next slide has no writing because I'm pretty sure you know what you're supposed to write in your outline. Okay. Opposite poles will attract each other, right? If you have a north and a south, they'll come together. Okay? But like poles will repel each other. North and north will repel. South and south will repel. So like poles repel, opposite poles attract. Good there? Yes.
What was E?
Magnetic monopole. Are we good with the idea of a magnetic monopole, right? The prefix of a mono means what? One, right? So when we talk about a magnetic monopole, that would be something that only has a north pole or only has a south pole. And we've never found anything in nature that exists like that, which is different than when we talked about with charge, right? You can have just a positive charge and a negative charge, but you can't just have a north pole or a south pole. You've got to have both. All right. Next concept that we'll talk about a lot in the next couple of days when we talk about current is the magnetic field. The magnetic field, we introduced the idea of a field in the last section when we talked about electric field. The field is an area. It's a space around the magnet where it can influence the behavior of other magnetic objects, other magnetic things. And as you can see from this picture, we use lines to represent what would happen to stuff in that magnetic field. And the lines are arrows. And those arrows go from the North Pole to the South Pole. So the arrows represent the field, the area around the magnet where it can influence the behavior of other objects. And those arrows go from the North Pole to the South Pole, just like in the picture. Now, something to keep in mind, and this is a little bit confusing as far as this can be confusing with field theory in general. I don't expect you to be an expert on field theory right now, but the area around this magnet is the field of this magnet. This area is where it can affect other objects. Now you're saying, well, it's not affecting other objects. True. But that's not because the field doesn't exist. The area around the magnet, the field around the magnet, exists regardless of whether anything is in it or not in it. All right? What happens to objects depends as much on the field as it does to those objects in general. Here, right, I bring the magnet close to this, right, and nothing happens. Not because there's no field, but if I bring it here, right, it's attached to the other one, so, right, it affects this object, right. It's not because there was a field over here but not over here. It's more of a condition of, well, what was this? Was this object affected by the field? Okay? The field is just the area. What happens to things kind of depends on them as much as it depends on the field. Okay? Good there? One magnetic field that we deal with all the time is, oh, sorry. You don't have this picture, but in this situation here, these black lines are small pieces of iron. Iron is magnetic. We call them iron filings, all right? But if we allow those iron pieces if we allow those iron pieces, I was thinking, so
Okay.
I totally forgot the word I was going to say. If we allow those iron pieces to interact with the magnetic field, we see that they line themselves up just like the lines are drawn on the previous picture. Okay? So going from the North Pole to the South Pole, notice none of the lines ever cross, all right? They're all concentric to each other. They don't cross. They go there. More, go ahead.
Isn't that like a kid's toy thing?
Yeah, one of those things where like you can use the little magnetic pen and put like hair on
Yeah.
dolls and stuff like that. Like, you know, so if you go to Cracker Barrel, they still have those kind of things, you know. But
You don't know what that is? No.
I know what you're talking about.
That's
Lauren.
Am I the only one who had a child in here?
Wait,
Okay.
was the other one on water?
No, the other one was just it was just different kind of magnet, right? This is still the magnetic field, but in the horseshoe magnet, it's lined up a little different, but it still goes from one side to the other.
I was just wondering if it's on the water.
No, like this is just like it's just on a piece. It's just on a table, but those iron pieces are allowed to move in a way so they line up with the magnet itself. All right, good there? All right, next. A magnetic field that we deal with all the time is Earth's magnetic field. So what we have come to realize is that Earth produces a magnetic field that resembles a gigantic bar magnet, where it has lines that go from one pole to the other pole. Okay? But how it's set up is different than what we call it. We call this side of the magnet the North Pole because it points north. All right? But if it's pointing towards the north, that wouldn't be the North Magnetic Pole, right? Because the North Pole of this magnet is attracted to what? The South Pole of other magnets. So what we call the North Pole of the Earth is really the South Magnetic Pole. If Earth was like a bar magnet, right? We would draw the S up here on the top because the North Pole of other magnets is attracted to it. And we would draw the N down on the bottom because the South Pole of other magnets is attracted to it. All right? So, Andrew, to your question, right, what we refer to as the North Geographic Pole is really the South Magnetic Pole. Okay? And those poles, the South Magnetic Pole, is not on top of the Earth. It's not where we call the North Pole of the globe. happens like in like northeastern Canada, like those those islands that are kind of up there that are part of Canada. That's really where the pole is, and the south geographic pole isn't where the north magnetic pole is. It's in Antarctica, but it's not on the very bottom. Okay? Good there? All right. What we also figure out is that over time, okay, over time, we have seen a shifting of where the Earth's north magnetic pole and south magnetic poles are. That Earth's magnetic field reverses itself over geologic time. We know this thanks to something that you guys learned about last year, right? Are we familiar with seafloor spreading and plate tectonics and stuff?
Yeah, that was
Right.
seventh grade.
Seventh grade. So okay, looking good.
So the north part actually points south.
So the north pole of this magnet, right, points towards the top of the Earth, but that means that the top of the Earth has to be the south pole of Earth. Does that make sense? Because the north pole of this magnet is attracted to the south pole of other magnets. Does that make sense?
Oh, I get it.
It's pointing north, but that's because that's the south pole, south magnetic pole. If we think of Earth, here, let's go back to this, we'll go back to this picture here, right? That you have this picture, right? If we think of Earth as a big bar magnet, right? If this compass points north, we call the tip of that arrow the north pole of that magnet. But because it's pointing north, the south pole of Earth as a big magnet has to be on the top because that's where the north stuff is attracted to.
Yeah.
Okay. All right. What we find out is that Earth's magnetic field actually flips-flops back and forth. Where the south pole is, where the north pole is, where the south pole is, where the north pole is. We know this because of the idea of seafloor spreading and plate tectonics and stuff like that, right? Magma comes up through the center, right? And there's a big mountain range right in the middle of the ocean, yes, right? And magma comes up, and we make new rocks, and then those rocks cool and they spread out. Does it all sound familiar? Yes, right? Okay. Good, good.
You know how the Earth's magnetic field is right now?
Right now, it's set up, well, the way that we call it is the south pole is up north and the north pole is out south. But what we find out, Julian, is that if you look at rocks in the floor of the ocean, especially rocks that contain iron, what we find out is that for a large stretch, they're oriented where all the north poles face one way. But after a while, they flip, and all those rocks show the north pole pointing the other way because the magnetic field of the Earth has flipped back and forth. Okay? What we find out, hold on a second, let me finish this slide at least, is that if we look at the track record and how long it takes for the field of the Earth to flip back and forth, we're kind of in a spot where it probably should flip again, where what we call the south magnetic pole should flip back over and come to the other side. I don't know if it happens like this, like I don't know if like tomorrow we'll wake up and all of our compasses will be wrong, I don't know. But yeah, I don't know how long it takes actually for that switch to occur. Yeah. All right, we'll finish this up on Monday and then continue on with inducing currents in conductors. Oh, one last thing. Hey, if you check the calendar, right now, there is no homework in this spot, but there will be by the end of the day, so check it out.
God.